Hello everyone and welcome. This is General Chemistry 2, lecture number 20. This is on entropy, spontaneity, and Gibbs free energy. This covers OpenStax sections 12.1 through 12.4, as well as section 13.4. First, let's start with a brief review on enthalpy. So enthalpy is something you should have learned about in General Chemistry 1 if you're using the OpenStax textbook. This would be in chapter 9 on thermochemistry. We've also touched on enthalpy a lot earlier in this course, so remembering that enthalpy generally refers to heat at constant pressure. Here we have two different energy diagrams being shown, where enthalpy, or basically the heat in joules, is on the y-axis, and then the progression of the reaction is shown on the x-axis. Here we have the energy diagram for an exothermic reaction, where delta H is less than 0. Here we note that the products have less energy than the reactants, so though we do have an activation energy to overcome, indicated here by EA, the overall energy is released in the course of this reaction. However, here, with an endothermic reaction where delta H is greater than 0, we should note that the products have more energy than the reactants. So not only do we have an activation energy barrier to overcome, but we have to overall input energy into this reaction for it to proceed. So we could describe this first reaction as being a, quote, downhill reaction, meaning that overall it flows downhill. The products, because they have less energy than the reactants, we could say that the products are more stable than the reactants. So this reaction could generally be described as favorable. Exothermic reactions are generally favorable, whereas endothermic reactions, we could describe them as being uphill reactions. The products are less stable than the reactants because they have more available energy to be used, and so this reaction can be described as an unfavorable reaction. So we're going to use these ideas to further describe a new term referred to as entropy. Entropy uses the symbol S, and generally speaking, entropy is a measure of the disorder of a system. It can also be thought of as randomness, dispersal, or freedom of motion. So as a system goes from being ordered to being disordered, we can say that its entropy is increasing. Let's look at a concrete example. Suppose we melt some water. So we have solid water, maybe some ice cubes. We leave it, in our glass on like a hot summer day, and it melts and goes from being a solid to a liquid. Is the change in entropy positive or negative for this phase change? We should note here that the system is becoming more disordered. Right? Solids are very packed in, they're very ordered, very compact, whereas liquids are much more disordered, they're much more free flowing, they'll take the shape of the container that they are in. So here the compound is becoming more disordered, or generally speaking, we could say that this system is becoming more disordered. The disorder is increasing, or you could say the order is decreasing. The point being is that this is an increase in the entropy. So we would say here that the change in entropy is positive. What about the change in enthalpy? What is the change in enthalpy here? Where we're going from a solid to a liquid. So to go from a solid to a liquid, we would need to add heat to this system. So we should say that the change in enthalpy should also be positive. We must add heat to melt the substance. So this is a reaction where both the change in entropy and the change in enthalpy would be positive. Here are a few more concrete examples. All four of these show the entropy increasing, or we can say that delta S is greater than 0. So going from a solid to a liquid, that's an increase in entropy. From a liquid to a gas, also an increase in entropy. Here, going from a packed-in ordered system where all of the gas is on one side of the container to a more disordered system where the gas is dispersed throughout both containers, this is an increase in entropy. Here, dissolving a solute in a solvent, this is an increase in entropy. Here, initially, they are separated. They are in their own spaces, especially that solute is nice and packed in and ordered. When it dissolves, it gets dispersed. These compounds, they get all mixed together. They are much more disordered. So this process represents an increase in entropy. Or heat being dispersed between two different objects. Here, it's more ordered. One object is hot, one is cold. We're bringing them into contact with one another. The heat disperses between the two, transfers between the two until they are approximately the same heat. Here we could say this system is more disordered. The heat is more distributed throughout both objects. So all four of these, going from left to right, show the entropy increasing, or again, to be more quantitative, we say that delta S is greater than 0. So let's predict the sign and magnitude of delta S. So for all of the processes listed below here, the entropy increases, or delta S is greater than 0. It's positive for all of these. The entropy would decrease, or delta S is less than 0, negative for the reverse. So temperature increases, this is an increase in entropy. Volume available for a gas to expand into, going from a solid to a liquid, liquid to gas, or especially from a solid to a gas, a substance dissolving in or mixing with another substance, a reaction that produces more free particles than it started with, or more specifically, a reaction producing more moles of gas than it started with. So all of these, again, represent an increase in entropy. Let's try an example problem. Is the change in entropy, delta S, positive or negative? And then is it small or large for the following reactions? So look at this reaction down below here. First question, is the change in entropy positive or negative? And then second, would you expect that change to be small or large? Go ahead and pause the video and see if you can come up with an answer here. Okay. Correct answer first, is the change in entropy positive or negative? You should have found that the change in entropy is negative. On the left side, we have 1 mole of gas. On the right side, 0 moles of gas. So the moles of gas decreasing. Thus, the system is becoming more ordered. See, we have a gas on this side, which is very disordered, very chaotic. On this side, we have nothing but solids, and solids are very ordered. So the system's entropy is decreasing. Delta S would be negative, and I would expect that to be a large change. This deals with that last bullet point right there. Let's try a couple more. For each of the following examples, choose whether or not entropy increases or entropy decreases, and whether delta S is greater than 0 or delta S is less than 0. So again, please pause the video and give these 4 problems a try. All right, correct answers are given below. So for the first two, these would both result in a decrease in entropy, where delta S is less than 0. Last two, increase in entropy, where delta S is greater than 0. The ones I want to hit on that maybe are a little more challenging were B and C. Letter B here, it says sucrose crystals precipitating from a saturated solution. Remember that if something is precipitating, that means a solid is falling out of a solution. So sucrose here is going from being a dissolved compound, being aqueous, to being a solid. So going from aqueous to solid, definitely a decrease in entropy. Here, heating hydrogen gas from 60 to 80 degrees Celsius, anytime you increase temperature, you're increasing the entropy. The system, the molecules are moving around more quickly. They are more disordered. So that's an increase in entropy for letter C there. All right, next let's briefly remind you about the first law of thermodynamics. So you learned about this all the way back in Gen Chem 1, and it states that energy can be converted from one form to another and can be transferred from a system to its surroundings, but it cannot be created or destroyed. New to the second law of new to us in Gen Chem 2 is the second law of thermodynamics. This one states that a system undergoing a spontaneous process will always proceed in the direction that causes the entropy of the system plus the surroundings, that is to say, the total entropy of the universe, to either increase or remain constant. So what this means is that delta S system, the change in entropy of the system, plus delta S surroundings, equal to the change in entropy of the surroundings, will always be greater than or equal to 0. This concept can also be seen as the era of time. Basically, it tells us that the entropy of the universe is always increasing over time. All right, so let's look at where this derivation of the second law of thermodynamics comes from. So technically, the change in entropy is defined as delta S equals Q over T. Now recall that in Gen Chem 1, when heat is transferred from a system to its surroundings, then negative Q system equals positive Q surroundings. Now if T is greater than 0, we can safely say then that the change in entropy for the system is less than 0, since right? Delta S system would be Q over T, and if Q is negative, then delta S must be negative. Similarly, we can say that delta S surroundings must be greater than 0 since Q surroundings is positive. Now remember that heat transfer in this direction only happens if the temperature of the system is greater than the temperature of the surroundings. So what this means is the system needs to be hotter than the surroundings for heat to be transferred from the system to the surroundings. Basically, right, heat is transferred from a hot object to a cold object. So what this tells us then is that the overall magnitude of Q system over T system must be less than Q surrounding over T surrounding. How do we know this? Well, again, if these Q values are the same as one another, but heat transfer only happens if the temperature of the system is greater than the temperature of the surroundings. If this number is greater than this number, then we can safely say then that this fraction, this value, must be less than this value. And this tells us then, substituting this back in here, that delta S system must be less than delta S of the surroundings. So what this means then is that delta S system plus delta S surroundings is always greater than or equal to 0, right? If the system has a negative entropy and the surroundings has a positive entropy, but the entropy change of the system is always smaller than the entropy change of the surroundings, we can safely derive this value right here. So this again tells us that the change in entropy of the system plus the change in entropy of the surroundings is always greater than or equal to 0. The total entropy change of the universe can never be negative. It is always 0, or more likely, it's greater than 0. All right, so now let's define this idea about a spontaneous process. You may have noticed this word earlier in the slides. We also used it a little bit in the previous lecture on electrochemistry. So a spontaneous process is a process that naturally occurs in only one direction under a given set of conditions. Spontaneous here in thermochemistry does not mean that it happens quickly or that it's surprising or it's instantaneous, right? The way we typically use the word spontaneous in everyday life. Spontaneous simply means that it will occur naturally under a given set of conditions. It will occur without any adding any energy from the surroundings. It'll occur without external influence. So for example, if you go, up to the top of a mountain, you put some skis on and you stand right at the edge of a slope, eventually you will begin spontaneously flowing downhill without any external influence. Just because of the set of conditions, that process will occur naturally. So water flows downhill under the influence of gravity. That's part of the conditions here. Ice melts if the ambient temperature is greater than 0 degrees Celsius. Iron will turn into rust over time if oxygen is present. Milk added to coffee will disperse uniformly if molecular motion is greater than 0. So all of these are examples of processes that occur spontaneously. They occur without any external influence, without extra energy being added from the surroundings. They will just occur naturally based on the conditions they exist in. And again, spontaneity is not related to how fast the process occurs. For example, radioactive isotopes, they decay spontaneously, but some of the processes may take thousands or even millions of years. Another note on spontaneity and reversibility. A process that is spontaneous in one direction is non-spontaneous in the reverse direction under the same conditions, and they are often irreversible under the same conditions. So if I dropped a vase and it shatters, this is an example excuse me, of a All right, sorry about that cough and that brief pause there. I had a little bit of a tickle in my throat. Okay, so again, this process is spontaneous and it can also considered to be irreversible under the same conditions, right? The vase will not magically put itself back together. We can't reverse time. Or ice. If you place ice out on the counter at 25 degrees Celsius and a pressure of 1 atmosphere, it will melt and turn into liquid water. And this is a spontaneous process, and importantly, it is an irreversible process under the same conditions. All right, so spontaneous processes, one thing to note about them is that they always increase the entropy change of the universe. Consider water freezing at negative 10 degrees Celsius. This is a spontaneous process under these conditions in that if you put water in a freezer at negative 10, it'll freeze under those conditions. It'll happen naturally, spontaneously, without you having to do anything else to the water. We know this happens. However, what we learned about earlier is that if I were to go from a liquid to a solid, this is a decrease in entropy. So how is this process spontaneous then if it represents a decrease in entropy? Well, it's important to note here that this decrease is only for the water, which in this case we could consider to be the system. So the change in entropy of the system is negative. However, heat is given off by the water from that water to the surroundings, which will result then in an increase in the entropy change of the surroundings. And again, remember that delta S system plus delta S surroundings is always greater than or equal to 0. So this increase in the entropy of the surroundings must be enough to either get this value to 0, but more than likely it's enough to cause a positive value or a positive change in entropy for the universe. All right, so all these definitions are interesting, but how can we make this quantitative? How can we actually measure the entropy change of the universe? Well, if the change in entropy of the system is negative, if entropy is decreasing, then the change in entropy for the surroundings must be positive by at least the same amount. Now we can calculate the entropy change of the system by measuring the temperature of the system and the heat of the system. Now calculating the entropy change of the surroundings is trickier since the surroundings here include literally everything else in the universe. So we need to ask then, how are the surroundings related to the system? We're recalling a definition from calorimetry where, again, we defined this earlier, negative Q system equals Q surroundings. We also defined in Gen Chem 1 that Q, heat, is equal to the change in enthalpy at constant pressure. So Q equals delta H at constant pressure. Making that substitution, this means that negative delta H system is equal to positive delta H surroundings. This gives the law delta H surroundings, or the equation I should say, delta H surroundings equals delta H, or excuse me, delta S surroundings equals delta H surroundings over T surroundings equal to negative delta H system over T surroundings. So basically, I took this equation right here, and I plugged in delta H system, or I plugged in delta H over T. All right, a couple more definitions here. If T system equals T surroundings, so if they are roughly equal to one another, we can make this a little simpler. And we can say then that the enthalpy or the entropy change of the universe is equal to the entropy change of the system plus negative delta H system over T. So here what I did was this relationship we established here for the entropy change of the surroundings. I am taking this value and I'm plugging it back into the second law. When we rearrange this system or rearrange this equation and make some substitutions, we find that negative T delta S universe is equal to negative T delta S system plus delta H system. And we're doing a little bit of hand waving here, but it's a very useful substitution to make. So this law right here, or this current equation, is pretty useful. We've got the entropy change of the system, which can be measured easily. We've got the enthalpy change of the system, which can be measured easily. But this right here, this is a little more nebulous. Temperature times the entropy change of the entire universe. This, we're going to make a substitution, and this quantity is going to be referred to as Gibbs free energy. Gibbs free energy is defined with the variable g. So this is delta G system. It is the measurement of the spontaneity of a process, and it refers to any remaining free energy available to the system. So all of this work gives us this equation. Delta G system is equal to delta H system minus T delta S. This is probably the most important equation we're going to cover in this lecture, so get familiar with this equation right here. So this Gibbs free energy thing, free energy, it's the difference between the energy produced by the process delta H, and the energy lost to the surroundings, T delta S. For a spontaneous process, this is the maximum amount of work that a system can produce. For a non-spontaneous process, this represents the minimum amount of work or energy that needs to be input into this process in order for it to run. So free energy change can also just be generally viewed as a measure of its driving force. So when you have a negative delta G, or when delta G is less than 0, the process is spontaneous in the forward direction. If you have a positive delta G, the process is not spontaneous in the forward direction. You would need to input energy to get that process to move in the forward direction. However, it could be said that it is spontaneous in the reverse direction. If delta G is equal to 0, the process is at equilibrium, which is considered to be the energy minimum. And again, free energy here is the energy the system can use to do work after accounting for the change in enthalpy and entropy changes, as well as any heat lost to the surroundings. So think of delta G as a measure of spontaneity that can be measured for the system, taking into account both the enthalpy and entropy changes. Okay, let's look at an actual problem. Use the enthalpy and entropy data shown below to calculate the free energy change for this reaction at 298 Kelvin. So we have the equation C2H6 forms H2 plus C2H4. We are given the enthalpy change at 136.4 kilojoules per mole and the entropy change at 120.8 joule per mole Kelvin. So we'll use this to calculate delta G, and then we can answer the second question, will this reaction proceed spontaneously? So first question, letter A here, I want to draw your attention to something important. Pay attention to your units. Your enthalpy values, your delta H values, are almost always given in units of kilojoules per mole, whereas entropy is typically given in units of joules per mole Kelvin. So make sure you convert one of them. It's typically easier to convert the entropy value into kilojoules. So that 120.8 joule per mole Kelvin is 0.1208 kilojoule per mole Kelvin. Then I'll use this equation, so delta G equals delta H, 136.4, minus T, 298, times delta S, 0.1208. This is equal to 100.4 kilojoules per mole. So we find here that we have a delta G value that is positive 100.4 kilojoules per mole. Second question, will this reaction proceed spontaneously? A positive delta G value means it is not spontaneous in the forward direction. All right, so let's just clarify these terms one more time. Delta G is Gibbs free energy. It represents the change in overall energy. It considers and takes into account both the enthalpy and entropy changes. If delta G is less than 0, we can refer to it as being an exergonic reaction, which means that it is spontaneous and it can do work on the surroundings. If delta G is greater than 0, this is considered to be an endergonic reaction, meaning it is non-spontaneous, it needs work input. And then reviewing enthalpy, remember delta H is the change in enthalpy, which is measured as heat transfer. If delta H is less than 0, this is an exothermic reaction. Heat is released to the surroundings. If delta H is greater than 0, this is an endothermic reaction, where the reaction or the system absorbs heat from the surroundings. And then finally, what we covered today, delta S is the change in entropy. Entropy can generally be considered to be randomness, disorder, or freedom of motion. So if delta S is less than 0, the system is becoming less disordered, or we could say more ordered, meaning there are fewer free particles. If delta S is greater than 0, the system is becoming more disordered. There are more free particles available. All right, and this table summarizes these three variables and their relationship to one another. And so what can be helpful here, and what you may be asked to do, is predict the spontaneity of a process purely just based on the sign of delta H and delta S, but not given any actual values. So there are 4 different scenarios. If you have a reaction that is exothermic, and so it has a negative delta H, and it results in an increase in entropy, so a positive delta S, both of these things represent favorable processes, and if you think about it, if delta H is negative, this term is negative, and if delta S is positive, this entire term will also be negative. You add two negatives together, you get a negative value, and so delta G must be negative, meaning delta G is spontaneous. So anytime you have a process that is both exothermic and it results in an increase in entropy, it is always spontaneous. On the flip side, if you have a reaction that is endothermic with a positive delta H and it has a decrease in entropy, if this term is positive, and then if this term is negative, the negative times a negative makes this term positive, so two positive terms being put together results in a positive delta G. The process is non-spontaneous. So anytime you have an endothermic reaction with a negative entropy change, it is always non-spontaneous. The two cases that are in between, if the process is endothermic, but it also has an increase in entropy, it depends on the temperature. It will likely be spontaneous only at a higher temperature. So if this term is positive and this term is negative, if this term can win, so to speak, if that temperature value gets big, it makes the negative term bigger, which makes this term win out over the positive delta H value here. So in this situation, the system is considered to be, or the reaction is considered to be spontaneous only at high temperatures. And then on the flip side, if the reaction is exothermic but it has a negative entropy change, it is spontaneous only at lower temperatures. All right, and here we show a couple real life examples of each of those processes. So the combustion of propane, it is both exothermic and entropy increases. It's always spontaneous. The formation of ozone is endothermic and the entropy decreases, so it's always non-spontaneous in this direction. Dissolving salt in water, it's an endothermic process that requires the input of heat, but it also increases entropy, meaning that it will be spontaneous at higher temperatures, and this makes sense given what we learned about solubility earlier in this course, where the solubility of these compounds often increases at higher temperatures. When water freezes, this process is exothermic, it releases heat. However, it also results in a decrease in the entropy, so it is only spontaneous at lower temperatures, and this makes sense given we know that water tends to freeze at low temperatures. Next, we're going to look at something called the crossover temperature. So a process that is spontaneous at one temperature but non-spontaneous at another will have a crossover temperature where the sign of delta G changes. So here we have an example of process A that's always spontaneous, so it doesn't matter what the temperature is, always spontaneous. Here, process B, we have an example of a process that is only spontaneous at low temperatures, and this right here would be considered to be the crossover temperature, where it changes from being spontaneous to non-spontaneous. Process C is an example of a process or a reaction that is always non-spontaneous. And then here, process D is an example of a process that is only spontaneous at high temperatures. So here we can see the crossover temperature, where it changes from non-spontaneous to spontaneous, is given here. So you may be asked to calculate these. If we know the values of delta H and delta S for a reaction, we can calculate the temperature above or below which the reaction will be spontaneous. You can do this by simply setting delta G equal to 0, plug in the known values, and solve for T. And you would find that T should be equal to delta H over delta S. And again, please make sure you pay attention to your units here. Enthalpy and entropy are typically in different units. So let's practice. A reaction has an enthalpy change of delta H equals plus 100 kilojoules per mole, and an entropy change of delta S equals plus 250 joule per mole Kelvin. First question, is this reaction spontaneous at room temperature? Second question, if not, in what temperature range will the reaction become spontaneous? Let's look at question A. We can use the equation delta G equals delta H minus T delta S. The enthalpy change is plus 100 kilojoules per mole, so we could input that as 100,000 joules per mole. The temperature is 25 Celsius, which we can plug in at 298 Kelvin. and the entropy is 250 joule per mole Kelvin, so we plug that value in. When we solve, we find that delta G equals 25,500 joules per mole, or that'd be about 25.5 kilojoules per mole. So we can see that at this temperature, delta G is positive, so the reaction is not spontaneous. So then second question, if not, in what temperature range will the reaction become spontaneous? You're being asked here to find the crossover temperature. So set delta G equal to 0 and then solve for T. When you do so, you should find that T equals delta H over delta S. And if we plug the values in that we were given, 100,000 joules per mole for delta H and 250 joule per mole Kelvin for delta S, you should find that T equals 400 Kelvin. What this means then is that the reaction becomes spontaneous at temperatures above 400 Kelvin. All right, next we're going to slightly change gears and we're going to learn how to calculate delta G naught. Remember, this little symbol right here is referred to as a naught and it means standard. So in Gen Chem 1, we learned how to calculate delta H naught values for a reaction by summing the standard enthalpies of formation for the products and the reactants. So this formula may or hopefully looks familiar to you, and we can calculate delta G as well as delta S the same way. So if we have a reaction given here, the change in free energy is calculated as the sum of the free energy of the products minus the sum of the free energy of the reactants. So it's still products minus reactants, just like you learned when using these delta HF values in Gen Chem 1. So let's look at an example. Use the data in the table below to calculate delta G naught for the reaction shown at 298 Kelvin. So we have C2H4 forms H2 plus C2H2. We've got a table of values given here. So if we set this up, let me get out my pen tool. So I would do the sum of the products minus the sum of the reactants. So delta G would be equal to the free energy change for H2. So the free energy change for H2 is 0. So this would be 1 times 0 plus, and where is this 1 coming from? It's coming from the coefficient right here. Remember that coefficients get multiplied, plus 1 times the delta G value, for C2H2, which is 68.4, minus the reactants, so the delta G value of C2H4, so that would be 1 times 209.2. And when you work this one out and solve, you should find that sorry about that. I just realized I made a small mistake here, and I flipped my values. Apologize for that. There we go. C2H2 on the product side is the 209.2, so it should be 209.2 right here. And then C2H4 is on the reactant side, 68.4. So 68.4 goes here. Apologies for that, my mistake. When you work this one out and solve, you should find that delta G is equal to about 141 kilojoules per mole, indicating the reaction is non-spontaneous under these conditions. Okay, let's quickly explain the difference between delta G, that Gibbs free energy we were looking at earlier in the lecture, and this delta G naught. So by definition, delta G naught measures the difference between the free energies of the products and the reactants under standard state conditions. Again, remember that's what this naught symbol, this little degree symbol means. It means standard state, which means 1 atmosphere of pressure, 1 molar concentration for solutions, and temperatures of 298 Kelvin. One thing to note here is that most reactions are not run using exactly these conditions. So delta G, the regular delta G, is like a snapshot. It tells us about the free energy change for the reaction under the current conditions. What this means is that there is only one delta G naught for a reaction, but there are infinitely many delta G values. It's kind of like how the way that Q and K worked when we looked at equilibrium. How K specifically referred to the concentrations at equilibrium. So there's only one K value for a reaction, but Q refers to the ratio of products to reactants under any conditions, so there were infinitely many Q values for a reaction. It's a similar idea here. And I again want to emphasize that the free energy change for a process is viewed as a measure of its driving force. So negative delta G means spontaneous in the forward direction. Positive delta G means non-spontaneous in the forward direction. When delta G is 0, the forward and reverse driving forces are equal. The process occurs in both directions at the same rate, which tells us the system is at equilibrium. So those are a couple of key things to remember here. And again, the only difference between delta G and delta G naught is that delta G naught is standard state. So 1 atmosphere of pressure for gases, concentration of 1 molar for solutions, and a temperature of 298 Kelvin. All right, now we're going to look at the relationship between free energy change for a reaction under non-standard conditions by using the reaction quotient Q. So the equation here, how we can relate thermodynamics to equilibrium, is this. Delta G equals delta G naught plus RT ln Q. So again, delta G is Gibbs free energy under the current conditions. Delta G naught is the Gibbs free energy at standard state, or at standard conditions. R is the ideal gas constant given here. T is the temperature in Kelvin, and then Q again is the reaction quotient Q. A derivation of this you may see. Remember that I just mentioned that if delta G is equal to 0, the forward and reverse processes are equal, meaning that you're at equilibrium. So if delta G is 0, Q must be equal to K, and this equation can be simplified to delta G naught equals negative RT ln K. All right, let's look at how this problem or how these equations can be used. So this question states, for the reaction shown below, the standard free energy change, delta G naught, is 33.0 kilojoules per mole. Calculate the free energy change for this reaction at 25 degrees Celsius given these current partial pressures. And the question asks, is the reaction spontaneous under these conditions? Okay, so we're going to want to use this equation here. Note that it says calculate the free energy change for this reaction. So it's asking you to solve for delta G. You are given delta G naught. R is a constant. You are given the temperature, and then you are given what you need to solve for Q. So we can use this equation. Delta G equals delta G naught is 33.0 kilojoules per mole, or 33,000 joules per mole, plus R, 8.314, times the temperature, 298 Kelvin, times ln Q. Let's go ahead and solve for Q. So Q would be the partial pressure of H2 cubed times the partial pressure of N2 divided by the partial pressure of NH3 squared. I'll plug in the values I'm given, 0.250 for H2, 0.870 for N2, and 12.9 for NH3. And I get 8.17 times 10 to the negative fifth. So this value is plugged in here. So the natural log of 8.17 times 10 to the negative fifth is negative 9.4126. So I plug that in. And when I work this out, I find that delta G equals 9,680 joules per mole, or 9.68 kilojoules per mole. And so the reaction is therefore non-spontaneous under these conditions. Letter B, calculate the free energy change for the same reaction at 800 degrees Celsius for a mixture containing 0.10 atmospheres of 0.10 atmosphere partial pressure of each gas. I'm not going to show the work for this one. So letter B, please go ahead and pause the video and see if you can come up with the answer for letter B. All right, and the answer you should have found is delta G is equal to negative 8.08 kilojoules per mole. And so yes, the reaction is spontaneous under these conditions. Okay, so let's analyze these relationships here. So the equation that we defined, let me back up a little bit. right here. So we took this equation, we said that when delta G equals 0, Q must be equal to K because we're at equilibrium, and thus we can define the modified version, delta G naught equals negative RT ln K. So now let's move to here. If K is greater than 1, what will delta G naught be? If K is less than 1, what will delta G naught be? And if K is equal to 1, what will delta G naught be? Let's analyze all three of these. First, if K is greater than 1, delta G naught will be less than 0. How do I know this? Well, if K is greater than 1, then this natural log, whatever you plug into this natural log, as long as you plug in a value that's 1 or greater, or specifically not 1 or greater. If you plug in a value greater than 1 into a natural log, you will always get a positive answer. So you've got a positive value, a positive value, a positive value, and then a negative. So you're always going to get a negative outcome here, which means delta G naught will be negative. This tells you that the reaction is spontaneous in the forward direction. And this makes sense, right? K is greater than 1. What did we learn about equilibrium constants? If K is greater than 1, that tells us the forward reaction is favored. The products are favored. What about if K is less than 1? Well, if you plug in any value less than 1 into a natural log, that value, that the output you're going to get is going to be negative. And so we have the negative from the natural log multiplied by this negative. Those two negatives cancel out, giving us an overall positive value. So delta G naught will be positive. It will be greater than 0, meaning the reaction is spontaneous in the reverse direction. And that again lines up with what we know about K. Finally, if K is equal to 1, what happens? If you plug in a value of exactly 1 here, the natural log is 0, which makes this entire thing 0. So delta G naught will be 0, and that tells us that neither the forward nor the reverse direction is favored. All right, let's practice relating K and delta G naught. So delta G naught is equal to negative RT ln K. That's our equation. Here, the problem states the KSP value for the dissociation of silver chloride is 1.74 times 10 to the negative 10th at 298 Kelvin. Calculate the standard free energy change for this reaction. All right, well, let's go ahead and work this one out. Delta G naught equals negative RT ln K, so we've got the negative sign out front. R is the ideal gas constant, 8.314 joule per mole Kelvin. T is the temperature given as 298 Kelvin. And K is 1.74 times 10 to the negative 10th, so we can plug that in here. And we find that delta G naught is positive 55,676 joules, or 56 kilojoules per mole. So note again that we have a positive delta G naught, which indicates that the reverse reaction is spontaneous. And again, this makes sense given how small this K value is, that the reaction prefers to go in the reverse direction. Let's look at a second problem. The standard free energy change for the reaction shown below is negative 199.7 kilojoules per mole. Calculate the equilibrium constant K for this reaction. So I would take this equation and rearrange to solve it for ln K by dividing the negative RT to the other side. So I get ln K equals delta G naught over negative RT. Delta G naught is negative 199.7, which would be negative 199,700 joules per mole, over negative 8.314 joule per mole Kelvin, times the temperature given as 298 Kelvin, and this is equal to 80.603. So ln K equals 80.603. Then to solve for K, we raise both sides by a power of E, so K equals E to the 80.603, and K is equal to 1.01 times 10 to the 35th, a huge K value. Note that the delta G naught value is an extremely negative value, which tells us forward reaction is strongly spontaneous. We also get a really big K value, and again, that big K value tells us the products are heavily favored. So these two interpretations line up well. All right, and we're going to end this lecture by looking at the relationship to electrochemistry. So in the lesson on electrochemistry, we learned how to calculate the amount of work that can be done by an electrochemical cell. We learned that work is equal to the number of moles times Faraday's constant times the cell voltage. So the Gibbs free energy of a reaction represents the amount of energy the reaction produces that is available to do work after heat transfer. So the way this cashes out then is that we can say that negative delta G naught equals NFE cell, or to flip it, delta G naught equals negative NFE cell. So basically, work here is being represented by delta G naught if we're going to use E naught cell, so standard. You could also the basic version of this would just be delta G equals NFE cell, but we typically work with standards here. So summarizing these equations, free energy, voltage, and equilibrium, we have the equation delta G naught equals negative NFE naught cell. So this is the standard free energy change and the standard cell voltage. Remembering that N is the number of moles of electrons and F is Faraday's constant, 96,485 Coulomb per mole. We also earlier defined that delta G naught equals negative RT ln K. So if we combine these two equations, if we set this equal to this, we get negative RT ln K equals negative NFE cell. And this rearranges to E cell equals RT over NF ln K. So all these relationships go together like this. We can now relate K, E, and delta G to one another with this triangle of equations. A negative delta G, a K value greater than 1, and a positive E cell. All three of these things mean products favored. So I get how this can be a little confusing and how these different variables have different interpretations. So to summarize, first we learned about equilibrium constants K, and remember that K is just the ratio of the products to the reactants, and so when K is greater than 1, it means the products are favored. Last lecture, we learned how E cell, when E cell is positive, it means that cell flows spontaneously in the forward direction. It means the reaction is giving off electrical work. So a positive E cell means the reaction proceeds spontaneously and the products are favored. And then today, we learned that a negative delta G means the reaction gives off energy. It's spontaneous in the forward direction, and again, the products are favored. So keep these three things in mind. Okay, that is it for today's lecture. I've got 4 practice problems here for you to try, so I strongly encourage that you pause the video and give these a try, and then in just a moment I'll go to the next slide and reveal the answers. All right, here are the answers. Oh, sorry, that might have been a little fast. Okay. So that's all for this lecture, and this was the second to last lecture of General Chemistry 2, just one remaining, Nuclear Chemistry. As always, I hope you found this informative and helpful and easy to understand. If you have any questions, please feel free to reach out to me via email or leave a comment down below, and I'll do my best to help out. But that's all from me. I hope you have a great day, and I'll see you in the next one.